Module 8, Lecture B, Responsible Deployment. By the end of this lecture, you will be able to evaluate competing models using metrics, plots, interpretability, and engineering consequences. Identify risks involving bias, imbalance, explainability, data drift, and unsafe automation. And design a responsible final machine learning workflow for a civil engineering use case. Responsible model selection. Model metrics. When comparing machine learning models, metrics should not be treated as a simple scoreboard. Each metric emphasizes different kinds of performance, and in civil engineering, the wrong error can be costly or dangerous. A model may appear accurate overall while still missing important defects, so it is better to examine how well it finds real problems, how often it raises false alarms, and how it performs under different conditions. Responsible model selection means choosing metrics that match the engineering decision and the consequences of each type of error. Model evaluation metrics should match the task and the real-world risk. Classification models may need high sensitivity when missing dangerous cases is costly, while other uses may require balancing detection with false alarms. Regression models should be judged not only by average error, but also by serious mistakes, such as underestimating extreme flood levels. For vision tasks like corrosion detection, performance depends on how well predicted damage areas match the actual areas, with precision needs varying by use case. Metrics are most useful when combined with visualizations, thresholds, and subgroup analysis. Overall performance can hide weaknesses in specific settings, such as certain sites, seasons, project sizes, or lighting conditions. Plots of predictions, errors, and missed detections versus false alarms help reveal reliability, while threshold choices should be guided by domain knowledge, risk, and stakeholder responsibilities. Python code. Model metrics. Responsible model selection means comparing metrics in light of real-world consequences. In civil engineering, different errors can carry very different risks, so the best model is not chosen by accuracy alone. Threshold choices also matter because they affect both inspection workflow and the chance of missing serious problems. The code imports two key Python libraries: NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the environment for analyzing data, evaluating model metrics, and displaying results clearly. The true bridge deck defect labels are stored as binary values, where 0 means no defect and 1 means a defect is present. In this dataset, the first 10 decks are defect-free, and the last 8 have defects. These labels provide the ground truth for comparing model predictions and evaluating performance. The risk scores for Model A are stored in a NumPy array, with each floating point value representing one instance's predicted risk. These scores are organized so they can be efficiently analyzed and used to evaluate the model's performance at different thresholds. A NumPy array stores Model B's risk scores for bridge deck defects, with each score representing one instance. The values range from low to moderate risk and will be used to test performance at different thresholds, helping compare how well Model B identifies serious defects against Model A. The code verifies that the true labels and both models' risk scores have matching shapes, so each score lines up with the correct label. This check helps ensure later metric calculations are valid. If the shapes do not match, the assertion stops the script and signals a possible data mismatch. This function evaluates model performance at a chosen threshold by turning scores into binary predictions. Scores at or above the threshold are treated as positive, and the rest as negative. It then counts true positives and true negatives by comparing those predictions with the actual labels. The evaluation counts false positives as cases where the model predicts a positive label, but the true label is negative, and false negatives as cases where it predicts negative when the true label is positive. Accuracy is the share of all predictions that are correct based on true positives and true negatives. Recall measures how well the model finds positive cases by comparing true positives with all actual positives, while guarding against division by zero. The code measures precision as the share of predicted positive cases that were actually correct, while guarding against division by zero. It then returns key performance metrics, including accuracy, recall, precision, false positives, and false negatives, to summarize how the model performs at a chosen threshold. Set a threshold of 0.5 to evaluate both models. For each model, use the metrics at threshold function with its risk scores to calculate measures such as accuracy, recall, and precision. Store the results together so the two models can be compared at the same threshold. The code prints a short report of model performance at a threshold of 0.5. It goes through each model's stored results, extracts the key metrics, and displays accuracy, recall, and precision rounded to 2 decimal places. This gives a quick comparison of how the models perform under the same threshold. The code reviews each model's results and reports how many serious defects it missed. This turns performance metrics into a practical engineering measure, highlighting which models are better at avoiding missed critical defects. We evaluate alert thresholds from point 2 to point 7 and count how many serious defects each model misses at each level. For both Model A and Model B, the metrics at threshold function is used to extract the false negatives, which represent missed defects. This lets us compare how the two models perform across different threshold settings. A new Matplotlib figure is created as the plotting canvas. Then missed defects are plotted against alert thresholds for two models. Model A is shown with circle markers, while Model B uses square markers, making their performance easy to compare. The horizontal axis is labeled to show that it represents the alert threshold for serious cracking. The plot is labeled to show missed serious defects on the vertical axis and is titled to emphasize how metric choice can reveal engineering consequences. A light grid improves readability, and a legend helps viewers distinguish the different model lines. The script ends by using Matplotlib's show function to display the completed plot. The plot helps compare two models by showing how different alert thresholds affect the number of missed serious defects. The script compares two bridge deck defect prediction models using risk scores and standard metrics such as accuracy, recall, and precision at a threshold of 0.5. It also counts how many serious defects each model misses, focusing on the engineering impact of false negatives. A plot shows how changing the threshold affects missed defects, helping balance inspection workload against the risk of overlooking damage. Interpretability insights. Interpretability is essential for choosing models responsibly because high-performance scores do not always show whether a model is safe or trustworthy. In civil engineering, predictions should be based on meaningful evidence, such as cracks or corrosion, not shortcuts like shadows or camera angles. When errors have serious consequences, a slightly less accurate model with clearer, more stable reasoning may be the better choice. Interpretability methods help reveal why a model makes predictions, such as showing influential image regions, important tabular features, or similar training examples. These explanations do not prove a model is trustworthy, but they provide evidence that experts should interpret alongside data checks. In model selection, interpretability helps confirm that performance comes from meaningful patterns rather than misleading signals. Interpretability matters when model results must be explained to non-experts, especially in public decisions like road repairs or flood damage assessment. Engineers need to connect recommendations to observable conditions and sound professional judgment. A more complex model may find subtle problems, but unclear explanations can require more human review. The goal is to choose models whose predictions, limits, and role in expert workflows can be understood, supporting responsible and safer deployment. Python code interpretability insights. Interpretability helps engineers choose models responsibly by making their behavior easier to compare. In this example, transparent hand-built scores show how each feature contributes, which can reveal possible shortcut reasoning. We import 3 common Python libraries for data work: NumPy for efficient numerical calculations, pandas for working with tabular data, and Matplotlib pyplot for creating visualizations. Together, they support computation, data analysis, and plotting results. A small bridge inspection dataset is created in a pandas data frame, where each row represents one inspection case and each column stores a feature. The data includes crack size, spall area, shadowing effects, and a binary label for whether deterioration is severe. This structure makes it easy to analyze the cases and compare scoring models later. Two scoring models assign different weights to damage features. The engineering model emphasizes structural damage, giving the most weight to crack size and spall area, with only a small role for shadow score. The shortcut model does the opposite, relying heavily on shadow score, while giving less weight to physical damage, which may reflect dependence on misleading visual cues. We first choose the key damage features, such as crack size, spall area, and shadow score, and place them in a separate feature set. These values are then normalized by comparing each one to its feature's minimum and range, scaling everything between 0 and 1. This makes the features easier to compare fairly, without larger measurement scales dominating the analysis. The function takes a set of feature weights and uses them to calculate a model score for each case. It aligns the weights with the scaled feature data, multiplies each feature by its matching weight, and then adds the weighted values across each row. The result is one weighted score per case. We score each case twice, once with the engineering weights and once with the shortcut weights, by combining the scaled features with each set of weights. Each score is then turned into a binary prediction using the same threshold of 0.45. Scores at or above the threshold indicate severe deterioration, while lower scores do not. This makes the two models easy to compare against the true labels. We measure each model's accuracy by comparing its predictions with the true severe labels and finding the proportion that match. This is done for both the engineering model and the shortcut model. The two accuracy scores are then printed in a clear format, rounded to 2 decimal places. The analysis focuses on the fourth case in the dataset, which is labeled as severe deterioration. For this case, feature contributions are calculated for both the engineering model and the shortcut model by combining the scaled feature values with each model's weights. The results then identify which feature contributes most to the severe score in each model, allowing the top driver of the prediction to be compared across the two approaches. We organize the previously calculated contribution values into a new dataset, with one column for the engineering model and one for the shortcut model. This makes it easier to compare how the two models assign feature importance for the selected severe deterioration case. A bar chart is used to compare how different input features contribute to the severe score for one bridge deck case. The chart is titled as an interpretability check with clear axis labels for feature inputs and their score contributions. The layout is adjusted for readability before the plot is displayed. This script compares two bridge inspection scoring models to show how interpretability affects evaluation. It builds a small dataset with damaged features, normalizes them, applies different feature weights, and checks how accurately each model predicts severe deterioration. For one high-risk case, it identifies which feature drives each model's score the most and visualizes those contributions. The main point is that models with different weightings can make similar predictions while relying on very different reasoning. Operational consequences. When a model moves into real-world use, accuracy alone is not enough. Teams must consider what errors cost, who is affected, and how the system supports organizational priorities. A pavement deterioration model, for example, must balance missed critical repairs against false alarms that waste resources and reduce trust. The best model is the one whose trade-offs fit the organization's responsibilities, not simply the one with the highest score. When deploying a model, consider both its technical demands and how people will use it. More complex models may improve accuracy, but they can require special hardware, high-quality data, frequent updates, and clear review processes. A model is only useful if its predictions are timely, understandable, affordable, and easy to integrate into existing systems. When assessing a model's real-world impact, consider how its performance may change over time as conditions, infrastructure, and practices evolve. A model that works well today can become less reliable if the environment shifts or new equipment is introduced. Sustainable use requires ongoing monitoring, detection of performance drift, and clear decisions about when humans should intervene. The key issue is not only technical performance, but also safety and accountability. Python code, operational consequences. Compare models by their real operational consequences, not just by simple performance metrics. In civil engineering, different errors can have very different costs, so a model that looks good on paper may still create serious field risk. We start by importing NumPy for efficient numerical calculations and data handling, and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the script to analyze data and compare model performance visually. A dictionary is used to store confusion matrix counts for two classifiers, Model A and Model B. Each model is described by its true positives, false negatives, and true negatives. Model A has 42 true positives, 18 false positives, 8 false negatives, and 132 true negatives, while Model B has 36 true positives, 6 false positives, 14 false negatives, and 144 true negatives. These counts provide the basis for comparing their classification performance. We assign financial costs to two model errors. A false alarm costs $1,200 because it triggers unnecessary action, while a missed failure costs $25,000 because it leaves a real problem unaddressed. These costs help evaluate models by their business impact, not just by accuracy. We prepare 3 empty lists to collect each model's name, accuracy, and estimated operational cost. As the models are processed, these values will be added so their performance and costs can be compared easily. For each model, accuracy is calculated from its confusion matrix. The total predictions are found by adding all entries, and the correct predictions are the true positives plus the true negatives. Accuracy is then the correct predictions divided by the total, showing how often the model predicts correctly. For each model, the code estimates total operational cost by combining the cost of false alarms with the cost of missed failures. It then records the model name, its accuracy, and its total cost. These stored values make it possible to compare the models side by side. The code presents a responsible comparison of models by printing a compact table of each model's accuracy and estimated consequence cost. It pairs the model names, accuracies, and costs together, then formats the results as percentages and readable dollar amounts. The result is a clear summary of both performance and cost implications for each model. To identify the model with the lowest operational risk, find the smallest operational cost using NumPy's argmin function. That position points to the model with the least financial consequence, which is then matched to its name. The result is printed as a clear recommendation for the lower risk model. Create a Matplotlib figure and axis with a 7 by 4 inch canvas. Then use the axis bar chart method to compare model accuracies by name. The bars are colored steel blue, and the y-axis is limited from 0 to 1, so the accuracy scale represents 0 to 100%. To show costs in dollars on a second axis, create a new y-axis that shares the existing x-axis. Then plot each model's operational cost with a dark red line and circular markers. Label the new y-axis as estimated consequence cost in dollars, so the added scale is clear. The plot is finalized by labeling the vertical axis as accuracy and giving it a clear title about headline accuracy and operational consequences. The layout is then adjusted to prevent overlap, and the visualization is displayed for viewing. This script compares two models for civil engineering decisions, where different errors have different financial impacts. It uses confusion matrix results to estimate both accuracy and the costs of false alarms and missed failures. Model A is more accurate, but its extra false positives make it more expensive overall, while Model B has lower accuracy but lower operational cost. The conclusion is that Model B carries less financial risk, showing that accuracy alone is not always the best basis for choosing a model. Risk and ethics. Bias and imbalance. Bias and imbalance in machine learning can make a model look accurate overall while failing for certain groups or conditions. In civil engineering, this can happen when training data is based on convenience, such as models that work on urban roads or one bridge type but perform poorly in rural, shaded, older, or coastal settings. The ethical concern is that these failures can lead to unequal maintenance and safety outcomes for underrepresented communities. Imbalance in machine learning can distort how risk is assessed. Class imbalance can hide rare but important outcomes, while geographic or temporal imbalance can make a model unreliable in places or conditions not well represented in the data. Social and institutional imbalances also matter, because data collection reflects human choices and priorities, not just the physical world. Bias and imbalance in machine learning should be handled as core design issues, not afterthoughts. Teams should examine what the data represents, what it misses, and whether the model works consistently across important subgroups. Domain experts can help reveal how data was collected and how predictions may affect real decisions, such as inspections or repair budgets. Mitigation may require better data or adjusted strategies so the model supports the right groups and reduces harm. Python code, bias and imbalance. Average accuracy can hide bias, especially when inspection data is imbalanced. To understand model risk more clearly, Engineers should examine subgroup metrics, which can reveal uneven performance across different parts of the data. The script begins by importing the main Python tools for data work. NumPy supports efficient numerical operations and arrays. Pandas helps manage and analyze tabular data. And Matplotlib's plotting module is used to create visualizations. Together, these libraries provide the foundation for data manipulation, analysis, and plotting. We create a small, reproducible inspection dataset by using a fixed random seed. The data is organized across 3 regions: urban, rural, and coastal. The planned distribution is 70 urban inspections, 20 rural inspections, and 10 coastal inspections, giving a known regional mix for easy inspection and testing. We create a list to store simulated inspection records. For each region, we use its assigned count to add that many inspection entries, with each entry recording the region. This produces a dataset whose inspections are distributed across regions according to the specified counts. Convert the rows into a pandas data frame to organize the data in a table for easier analysis. Then, use an assertion to check that the data frame has the expected number of inspection records, confirming the data loaded completely. A dictionary sets the true severe crack rate for each region: 10% for urban, 25% for rural, and 40% for coastal. Pandas then maps these regional rates onto the region column to create a new severe column for each inspection. This provides the baseline risk needed to simulate realistic defect data. Random values between 0 and 1 are generated for each row of the dataset. Each value is compared with the severe crack rate for its region to decide whether a true defect is present. If the value falls below that regional rate, the inspection is marked as having a severe crack, simulating defects according to regional risk levels. The setup defines region-specific miss rates to model how often true defects are overlooked: 15% in urban areas, 45% in rural areas, and 65% in coastal areas. It also uses a 5% false alarm rate for cases where a defect is predicted incorrectly. Together, these values simulate a bias detector with uneven sensitivity and accuracy across regions. The process simulates model predictions for each row of data and stores the results. When a real defect is present, a random check uses the region's miss rate to decide whether the model fails to detect it. When no defect is present, another random check uses the false alarm rate to decide whether the model incorrectly signals a defect. Together, these simulated outcomes reflect how the model behaves across different regions. The code stores the model's defect predictions in a new column for each inspection entry. It then compares those predictions with the actual defect values and uses the average of the correct matches to calculate overall accuracy for the dataset. The recall for group function measures how well a model detects severe defects within a subgroup. It looks only at cases where a true severe defect is present. And if none exist, it returns a not a number value, because recall cannot be calculated. Otherwise, it averages the model's defect predictions for those true positives to estimate recall for that group. The data is grouped by region, and recall is calculated for severe defects in each group to compare model performance across areas. The results are labeled as defect recall and organized into a simple table. A sample count is also added for each region, showing both performance and how much data supports it. The model's overall accuracy is printed first to give a quick sense of performance across all data. Then, subgroup recall is reported by region, including each region's sample count and recall value. This breakdown helps reveal performance differences that overall accuracy may hide, making subgroup metrics important for evaluating model reliability. We create a simple plot to compare subgroup representation by region. Using a 7 by 4 inch figure, we add a bar chart where each region appears on the x-axis, and each bar shows the number of inspection images from the summary data. The axes are labeled to make clear that the chart compares regions by their inspection image counts. A second y-axis is added to the existing plot, so recall data can be shown alongside the original graph. The recall values for severe defects are plotted by region, using circular markers and a crimson line to make them distinct. The new axis is labeled for severe defect recall and limited from 0 to 1 for clear interpretation. The plot title emphasizes that class imbalance can hide unsafe performance within subgroups, highlighting why subgroup metrics matter in model evaluation. The layout is then adjusted so the plot elements fit cleanly, and the plot is displayed for analysis or presentation. This script shows how biased and imbalanced data can hide poor model performance in specific groups. It simulates inspection results across urban, rural, and coastal regions, with uneven sample sizes, defect rates, and prediction miss rates. Overall accuracy may look acceptable, but subgroup recall reveals that some regions are much less reliably detected. The key lesson is to check subgroup metrics, not just averages, before deploying a model safely and fairly. Bias and imbalance. Bias and imbalance in machine learning can make a model look accurate overall, while performing poorly for certain groups or conditions. In civil engineering, this can happen when training data comes mainly from specific locations or well-documented projects, so the model misses important real-world variation. A pavement model trained mostly on urban highways may not generalize to rural roads, and a structural model focused on common defects may miss serious issues like corrosion. The ethical concern is that these failures can create uneven reliability and place greater risk on some communities. Data imbalance often begins during data collection, when common situations are recorded far more than rare but important events. As a result, models may perform well on average while missing critical anomalies or doing poorly for certain regions, income groups, building types, or older structures. To reduce this risk, it is important to check whose data is included or missing and evaluate performance across subgroups, not just with one overall score. Managing bias and imbalance requires both careful technical review and professional judgment. Teams should check whether datasets miss important cases and whether models perform reliably across key groups, not just overall. If weaknesses appear, they may need more data, better labels, or adjusted thresholds, while also considering how errors affect people and resources. Bias should be treated as an ongoing risk, not a one-time fix. Python code, bias, and imbalance. This example highlights hidden subgroup risk. Strong overall accuracy can still mask unsafe performance differences within specific groups. Civil engineers should therefore check subgroup results, not just the average outcome. The script begins by importing the main tools for data work in Python. NumPy supports efficient numerical operations and arrays. Pandas handles data manipulation with tables, and Matplotlib's plotting module creates visualizations. Together, these libraries prepare the script for data analysis and visualization. A random seed is set to make the results reproducible. The dataset is then defined with 80 urban highway images and 20 rural road images. Of these, 16 urban images and 10 rural images contain true defects, providing the ground truth for evaluating detection performance. A pandas data frame is used to organize road inspection data by subgroup. It compares urban highways and rural roads using columns for the total images inspected, the actual defects found, and the defects missed. This structure makes it easier to review and analyze inspection results for each road type. The code first checks that every group has at least one image, then confirms that missed defects never exceed the total true defects. These checks help ensure the data is valid before analysis. It then calculates detected defects by subtracting missed defects from true defects, giving the number correctly found in each subgroup for evaluating detection performance. Recall is measured for each road subgroup by comparing detected defects with the true number of defects, showing how well the model performs within urban and rural groups. Overall recall combines detections and true defects across all groups into one dataset level score. The imbalance ratio compares the largest subgroup image count with the smallest, revealing how uneven the dataset is and whether bias may be present. This check evaluates bias and imbalance in pavement distress detection by comparing overall defect recall with recall on urban highways and rural roads. It also reports the imbalance in image counts between the two groups. The key point is that average performance can hide weaker detection in rural areas, so subgroup results are important for understanding safety risks. The plot is set up with a figure and axes. Then a bar chart compares recall values across road groups. Urban and rural groups use different bar colors, so they are easy to distinguish. A dashed black horizontal line marks the overall recall, giving a reference for comparing each subgroup's performance. The plot is formatted to make subgroup recall easy to interpret. The vertical scale is set from 0 to just above 1. The y-axis is labeled defect recall, and the title emphasizes that subgroup performance can reveal imbalance risk. A legend is added so viewers can identify key elements such as the overall recall line. To finish the visualization, use Matplotlib's tight layout function to make the plot elements fit neatly, then display the plot. This lets you review subgroup performance and identify imbalance risk in defect detection. This script shows how overall accuracy in road defect detection can hide unequal performance across road types. Using a small dataset of urban highways and rural roads, it compares recall for each group and finds stronger detection on urban highways than on rural roads. It also measures the imbalance in image counts between the groups, showing that rural roads are underrepresented. The key lesson is that average results can mask safety risks, so subgroup performance must be checked to support fair and reliable defect detection. Unsafe automation. Unsafe automation occurs when machine learning systems make real-world decisions without enough human oversight. In civil engineering, this can affect safety, costs, and public trust, because predictions about issues like bridge damage or flood risk depend on the quality of the data and assumptions behind them. The key ethical concern is treating model outputs as final decisions, which can give flawed systems too much authority and lead to dangerous mistakes. Unsafe automation can create automation bias, where people trust model outputs too much, especially when they look precise or confident. This may cause engineers and managers to ignore local knowledge or accept recommendations that reflect uneven data, such as prioritizing well-monitored roads over neglected areas. Risk also increases when models are used outside their intended purpose, like applying a stormwater tool to future storms it was not designed to assess. The main concern is not only model accuracy, but whether the model's limits fit the importance of the decisions being made. Automation should support human expertise, not replace accountability. Responsible workflows clearly define what the system can decide, what requires human review, and when issues must be escalated. They should expose uncertainty, document data sources, explain key outputs, and allow recommendations to be questioned. In high-risk settings, Success depends not only on accuracy, but also on failure impact, detection speed, correction responsibility, monitoring, audits, training, and governance that protect safety, fairness, and human judgment. Python code, unsafe automation. This lesson shows why fully automated bridge inspection decisions can be unsafe. It compares automated outputs with a safer approach that includes human review, helping beginners understand the importance of oversight in critical infrastructure decisions. The script begins by importing 3 key Python libraries: NumPy for efficient numerical work, pandas for handling and analyzing structured data, and Matplotlib's plotting tools for creating charts and graphs. Together, these imports provide the basic tools needed for data processing and visualization. A small bridge inspection dataset is created using a pandas data frame, where each row represents one bridge labeled from A to F. For each bridge, the data includes crack size in millimeters, traffic volume in thousands, and the share of the bridge covered by sensors. These metrics provide a simple basis for comparing bridge conditions and supporting later analysis. The data is checked before analysis to make sure it is complete and the right size. It must include the required columns for crack size, traffic volume, and sensor coverage, and any missing columns trigger an error. A second check confirms there are exactly 6 rows matching the 6 bridges being inspected. Each bridge gets a risk score based on crack size, traffic volume, and sensor coverage, with each factor given a different weight. Crack size and traffic increase the score, while sensor coverage is also included according to its assigned weight. The score is saved as a new model score column in the bridge's data, where it can help identify bridges that may need urgent repair instead of routine monitoring. This code assigns each bridge an automated action based only on its risk score. If the score is at least 1.10, the bridge is marked for urgent repair. Otherwise, it is assigned routine monitoring. The decision rule is simple and does not account for any other factors. This code adds a safer decision workflow by creating a new safe decision column. It checks each bridge's sensor coverage, and if coverage is below 0.5, the case is sent for human review. Otherwise, the system keeps the existing automated decision. This helps ensure low data cases are not handled by automation alone. We summarize the bridge decisions by counting how often each automated decision type appears, then repeat the same count for the safer decision results. To measure escalation, we count the cases where the safer decision is human review and convert that total to a whole number. This gives both the distribution of decisions and the number of cases sent for human review. This example shows why unsafe automation is risky in bridge inspection triage. It compares decisions made by automation alone with a safer workflow that adds human oversight, especially when sensor coverage is low. The key lesson is that high-stakes predictions need data quality checks, escalation, and human review to reduce the risk of harmful automated decisions. To make bridge risk scores easier to interpret, each bar is colored by decision type. Bridges needing human review are shown in tomato red to signal attention, while routine cases are shown in steel blue. This makes it easy to spot bridges that may need further inspection because of low sensor coverage. The plot shows automated risk scores for different bridges as a bar chart, with colors indicating whether each case was escalated for human review. A horizontal threshold line marks the point where automation decisions change, making it easier to compare scores against the cutoff. Access labels, a title, and a legend clarify the bridge identifiers, risk scores, review status, and threshold, emphasizing how unsafe automation can hide low data coverage. This example shows why bridge inspection decisions should not rely only on automation. It uses bridge data such as crack size, traffic, and sensor coverage to calculate a risk score and flag urgent repairs. But it adds a safer workflow that sends cases with low sensor coverage to human review. The results compare automated decisions with this oversight-based approach, showing that poor data quality can require human intervention. The main lesson is that high-stakes predictions must account for uncertainty, not just risk scores. Responsible final workflow. Plan responsible workflow. In a responsible civil engineering workflow, a machine learning model should support, not replace, expert decision-making. Its purpose, data use, quality checks, and performance measures should be clearly defined with public safety and trust in mind. For example, a model used to prioritize culvert replacements should communicate its confidence and data limits, so engineers can apply it appropriately in real field decisions. A responsible civil engineering workflow should consider the full life cycle, from data collection through deployment and monitoring. Data from sensors, satellites, and other sources may contain errors, gaps, or bias, so teams should document where it comes from, check that it represents real conditions, and handle missing values carefully. Models should also be trained and tested under realistic conditions to ensure they are reliable enough to support responsible engineering decisions. Before deployment, teams must decide who reviews model outputs, who can override them, and how errors or uncertainty will be handled. High-risk decisions should involve human experts, and safety should never depend only on a model's prediction. After deployment, the system needs ongoing monitoring, regular checks, and updates as conditions change, so reliability, safety, and transparency are maintained over time. Python code. Plan responsible workflow. Before deploying civil models, plan responsible workflows that support accountable decisions. Use a readiness checklist to assess whether the deployment is prepared and governed appropriately. We import pandas to work with structured data and Matplotlib's plotting tools to create charts and visualizations. Together, these libraries prepare the script for basic data handling and visual analysis. A bridge model workflow should be checked against a concise readiness checklist before deployment. The key areas are clear intended use, data quality, bias and coverage, uncertainty communication, human oversight, and a monitoring plan. Together, these checks provide a structured way to assess whether the workflow is ready and responsibly managed. We define readiness scores from 0 to 1 for each workflow check, showing how fully each check has been addressed. These checks and scores are then organized in a pandas data frame, making it easier to analyze and visualize workflow readiness. The code validates the workflow data by confirming that every defined check has a matching score. It also ensures each score falls between 0 and 1, so the readiness assessment uses valid values. The code summarizes workflow readiness by averaging all check scores into one overall score. It then finds the lowest scoring check to identify the weakest area, showing which part of the workflow needs the most attention. The code summarizes responsible workflow readiness by showing an overall readiness score out of 1 and identifying the weakest area that needs improvement. It also reinforces that deployment should only happen when proper review, limits, and monitoring are in place to support safety and accountability. The The plot presents a horizontal bar chart of workflow checks, where each bar shows a readiness score. A red dashed vertical line marks the minimum target score of 75, making it easy to compare each check against the benchmark. The chart includes clear axis labeling, a descriptive title, a legend, and layout adjustments so the final visualization is readable and uncluttered. This script checks whether a bridge model workflow is ready for deployment by scoring key areas such as data quality and bias review. It stores the scores, calculates the average readiness level, and highlights the weakest area for improvement. It also presents the results in a horizontal bar chart with a target threshold, making it easier to see which checks need more attention before deployment. Ethical safeguards. Ethical safeguards in machine learning help ensure models are fair, transparent, and safe, not just accurate. In civil engineering, where models can affect decisions such as bridge inspections or flood risk mapping, these safeguards should be built in from the start. Teams should consider who may be affected, what harms could result from wrong or biased predictions, and which decisions should remain under human control. Treating social impact as part of engineering quality helps prevent models from reinforcing existing inequalities. Fair machine learning requires checking for bias and uneven performance across groups and settings. In civil engineering, this includes geographic and economic differences, such as whether models trained in cities work well in rural areas or in places with limited sensor data. Teams should track where errors happen, explain model limits to decision makers, and use strong data governance to protect sensitive information and prevent misuse. Ethical safeguards help ensure machine learning models are used responsibly after deployment. Their predictions should support human decisions, not replace them, especially in public safety contexts. Users need clear information about prediction confidence so they know when further review is needed. Ongoing error reporting, audits, and retraining help keep models aligned with safety and public trust. Python code, ethical safeguards. Ethical safeguards help ensure engineering systems are deployed responsibly. Even small audits can reveal unequal model performance, while human review supports safety and trust. The script imports 3 key Python libraries for data work: NumPy for efficient numerical operations and arrays, pandas for manipulating structured data, and Matplotlib pyplot for creating visualizations. Together, these tools prepare the script for data processing, analysis, and plotting. The setup begins by fixing the random number generation so results are reproducible. It then defines the bridge location categories as urban, rural, and underserved, and creates an empty collection to store simulated inspection records. Each record will later capture key details such as the area, bridge identifier, true risk, and predicted risk for analysis. The simulation creates data for 12 bridges in each area and assigns each bridge a true high-risk status using a probability of 0.35. It then applies different inspection miss rates by area: lower in urban areas, higher in rural areas, and highest in underserved areas. This models how inspection errors can vary across communities and reflect real-world disparities in accuracy. The model simulates whether a bridge is predicted as high risk, using the bridge's true risk and the error rates for its area. If the bridge is truly high risk, the prediction is based on the chance of correctly detecting it, which is 1 minus the miss rate. If it is not high risk, the prediction uses the area's false alarm rate, representing the chance of incorrectly labeling it as high risk. The code adds a new entry to a records list during each loop iteration. Each entry stores the area, bridge identifier, true bridge risk, and predicted risk, allowing the simulation to compare actual and predicted inspection outcomes across different areas. The data is organized by naming the columns for area, bridge identifier, true risk, and predicted risk, then creating a pandas data table from the records. A final check confirms the table has 36 rows and 4 columns, ensuring the simulated data was stored correctly. We evaluate the model by finding 2 key error types: high-risk bridges it missed and low-risk bridges it incorrectly flagged. Then we summarize results by area, including the total number of bridges, actual high-risk cases, missed high-risk bridges, and false alarms. This area-level summary shows where the model performs well and where it needs improvement. The code computes each area's miss rate by comparing missed high-risk bridges with the total number of high-risk bridges, while avoiding division errors when the total is 0. It then flags areas for review when the miss rate is above 25%. Any remaining missing values in the summary are filled with 0, so the data is complete. The audit output summarizes ethical safeguards for a bridge inspection model by comparing urban, rural, and underserved areas. It focuses on the rate of missed high-risk bridges in each area, then reports each area's miss rate in a clear format. It also indicates whether the results require further review, helping identify where follow-up action may be needed. This visualization uses a bar chart to compare the miss rate for high-risk bridges across urban, rural, and underserved areas. A dashed horizontal line marks the review threshold at 0.25, making it easy to see which areas may need attention. The chart is labeled, titled for pre-deployment error auditing, scaled from 0 to 1, and includes a legend for clarity. This script tests whether a bridge risk model performs fairly across urban, rural, and underserved areas. It creates simulated true and predicted failure risks, then measures missed high-risk bridges and false alarms for each area. The main focus is the miss rate for high-risk bridges, and any area above 25% is flagged for review. A summary and bar chart show where performance may be unequal, helping guide ethical deployment decisions. Human oversight. In civil engineering, machine learning should support professional judgment, not replace it, because decisions affect public safety and resources. Before using a model, teams should define who reviews its outputs, how confident the model must be before action is taken, and which decisions require human approval. This keeps accountability with trained professionals who can interpret predictions, such as bridge wear, flood risk, or concrete cracks, within the broader engineering context. Effective oversight in civil engineering means having clear ways to handle uncertainty, poor data, and unusual situations. When predictions are low confidence or conflict with field observations, the workflow should escalate the issue to human reviewers who can override the model when needed. Reviewers should also check whether recommendations, such as delaying maintenance, could reflect bias. The goal is to ensure model outputs are reliable, fair, and sensible in real-world conditions. Human oversight should be built into every stage of model deployment, not added only after problems appear. This means training users, keeping clear audit trails, and regularly reviewing performance with engineers and data scientists. Local experts can identify infrastructure conditions that data may miss, and teams should be ready to adjust automation when performance declines. The goal is to support professional judgment with machine learning, while keeping civil engineering workflows transparent and responsible. Python code. Human oversight. Human oversight helps keep automated systems accountable by having engineers review model recommendations when the system is uncertain. This example focuses on creating a checklist to guide that review process. We import pandas to work with tabular data and Matplotlib's plotting tools to create charts and visualizations. Together, these libraries provide the basic setup for data analysis and visualization in the script. The data is set up as a list of records for inspection recommendations. Each record describes a site with its name, risk level, confidence score, and whether an equity flag applies. For example, Bridge A is high risk with strong confidence and no equity flag, while Road B has lower risk, lower confidence, and an equity flag. These records will be used to decide oversight actions based on predefined rules. The snippet creates 2 inspection recommendation records for later analysis in a data frame. Slope C has moderate risk, low confidence, and no equity concern, while Culvert D has low risk, high confidence, and no equity concern. These records support further review and help determine oversight actions. The records are first converted into a pandas data frame, turning the list of dictionaries into a structured table with rows and column headers. An assert statement then checks that the table has 4 rows and includes the risk column. This quick validation confirms the data has the expected shape before any further work. The oversight action function decides what human review is needed for each data frame row. If the row's confidence value is below 0.6, it returns engineer review, meaning a human engineer should check the recommendation because confidence is low. The code flags a row for a bias check when 2 conditions are true. The equity flag indicates a possible fairness concern, and the risk value is below 0.6. When both are met, the recommendation is marked for further review to help ensure fairness. The code checks whether the current row's risk value is at least 0.8. If so, it treats the asset as high risk and returns the action urgent inspection, meaning it needs immediate attention. The function returns routine monitoring when no special oversight conditions apply to a row. In other words, if confidence is not low, equity-related risk is not flagged as low, and overall risk is not high, the case is handled through normal observation. This keeps extra actions focused only on cases that need special attention. The code applies an oversight action function to each data frame row, assigning an action based on the rules for that record. It then counts how often each action occurs and sorts the summary by action name for a clear overview. The process prints a brief introduction, then goes through each site and its assigned human oversight action. For each location, it displays the site name with the required action, creating a clear summary of decisions based on the model's recommendations. This creates a compact bar chart from the summary data to show human oversight actions. The chart uses steel blue bars, a clear title, and axis labels for the number of assets and the required human step. The x-axis labels are rotated for readability. The layout is tightened, and the plot is displayed. This script shows how human oversight can guide automated inspection recommendations. It uses a small dataset of sites with risk levels, confidence scores, and equity flags, then applies an oversight checklist to assign actions such as engineer review, bias check, urgent inspection, or routine monitoring. The results show the decision for each site, and a bar chart summarizes how many cases fall into each action type. In this lecture, you learn to evaluate competing models using metrics, plots, interpretability, and engineering consequences. Identify risks involving bias, imbalance, explainability, data drift, and unsafe automation. And design a responsible final machine learning workflow for a civil engineering use case. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.